Good afternoon. In today's session, we are supposed to study about the adaptive differential pulse code modulation. In previous session, we have seen about the differential pulse code modulations. Most of the time, the samples of informations are correlated with each other. So we can say there is a lot of redundancy in the signal. Meaning, it means what? There is a simple, similar information resides in two or the more adjacent samples. So, if we are using the pulse code modulations, we are transmitting the redundant information. So, instead of pulse code modulations, if we are using the differential pulse code modulations at that time, instead of sending the redundant information, we can predict its future value from its previous past values. These things we have seen in the differential pulse code modulations. So here we can say in the differential pulse code modulation, instead of transmitting encoded version of the sample, we can transmit encoded version of the difference between two consecutive samples. But we have seen when we were using the differential pulse code modulation, at that time also we will get the same error like a delta modulations. We will get the noise that is nothing but granular and the slope overload noise. Then we have seen about the delta modulations also. So in delta modulation, what we have seen, it is the system in which corresponding to each sample we will have send single encoded bit per a sample. So in pulse code modulation we are sending n bit per sample at a time. But in delta modulation, we are sending single bit per sample. So, delta modulator will transmit the binary output whose polarity depends on the difference between modulating and the feedback signal. So, we will get here the data, but it is simple hardware as compared to the pulse code modulation. If you see about the transmission error, it is more tolerant to the transmission error and it will not need the synchronization in the pulse code modulations. It is having lots of advantages over the pulse code modulations. Like it will consist of sampling block which samples the input analog signal. Here each sample is compared with the predicted version of the previous sample. And here the difference of the signal of parameter is nothing but we are taking this is as the differential modulation output. We are taking it. But here when we are supposed to use delta modulation, at that time also we will get two noises. These are nothing but slope overload noise and the granular noise. These two types of the quantization error are occurred in delta modulation and in the differential pulse code modulation. So now here we are supposed to study about the adaptive differential pulse code modulation. So here when we are using the adaptive differential pulse mode modulations, it will be the improved version of the differential pulse code modulations, because here we are supposed to incorporate an adaptive quantizer. It means what? Here we can take variable step size at the encoding. Instead of the same step size which we were taking in the differential, here we can take variable delta at the encoding. So here you can see the block diagram also for the adaptive differential pulse code modulation. The quantized prediction error. This is nothing but we are saying quantized prediction error which we are taking by using the adaptive error. Adaptive quantizer. We are saying that as a DQ of K. It is the good measure of the predicted version. This is nothing but predicted error size. So it can be used to change the delta, which will minimizes the value of DQ of K. And when we will get the fluctuation in the DQ of K, it will fluctuate around the large positive or the negative value in the predicted error. So here the prediction error is large and delta needs to increase. But when we are fluctuating the DQ of K, that will around the zero value or the small value. At that time we are supposed to need decrease the delta value to decrease. So here what we are saying, when we are supposed to use adaptive differential pulse code modulations, it will be the improved version for the differential. And what are the errors in the differential? We will get the quantization error like the slope overload and the granular noise. So here we are supposed to decrease. How we can decrease? If we are taking the variable step size, variable delta at the encoding. So here we are saying the quantized prediction error DQ of K is a good measure of the predicted error size. So we can use that to change the value of delta, which will minimizes the value of that prediction error, that is nothing but D of K. So when DQ of A fluctuates around the large positive or the negative value, we will get the error that will be high, but we will need that error to be less. So here delta needs to increase. But when DQ of K fluctuates around 0, we are supposed to decrease the delta. So here if we can see one example of the adaptive differential pulse code modulations. An 8-bit PCM sequence can be encoded into a 4-bit. That is nothing but adaptive differential pulse code modulations sequence at the same sampling rate. So this will decreases its channel bandwidth by 1 hop with no loss in the quality. You can see here when we are using ADPCM 4-bit instead of 8-bit PCM, we are not getting any loss in the quality, but we are supposed to transmit that data with the bandwidth that will be 1 half. You can see here in the diagram. When we are taking variable step size, at that time we are not losing any data, but we will get the output that will be the similar, but there will be no loss. So here when we are using the pulse amplitude, when we are using the pulse code modulations, pulse frequency modulations, pulse position modulations, pulse width modulations, or when we are doing the pulse amplitude modulations, you can see how we are taking the waveforms. When we are doing the modulations, that will be in the form of amplitude, in the form of width, in the form of position, in the form of frequency, or in the form of code modulations, how we are doing. So here now we have seen about the pulse code modulation, delta modulations. Then we have seen about the adaptive delta modulations, differential pulse code modulations, and adaptive differential pulse code modulations. Again, we can use the delta sigma modulations. It is nothing but in the delta modulations, we are taking the derivative of incoming signal. Then at the receiver 8, we can take its integration. It means what? In delta modulations, we are taking derivative of incoming signal, and at the receiver, we are doing the integration. It means what? We are accumulating the signal. If the signal is added with the noise, then demodulated signal is going to the accumulator due to the noise. To overcome this drawback, we are supposed to integrate the signal before doing the delta modulations. So this scheme we can say as a delta sigma modulations, which will give advantages over the delta modulations. Delta modulation means what? When we are doing the delta modulation, at that time we are supposed to take derivative of incoming signal, and at the receiver we are doing the integration. But if the signal is added with the noise at the demodulated signal, it will go to the accumulate due to the noise. So here when we are using instead of delta sigma modulations, it will eliminate the accumulate integration at the receiver. So we will get very simple circuit, and the low frequency contents of the input are pre-emphasized, and adjacent samples of the input to the delta modulator are more correlated with each other. So it will reduces the variance of the error signal, and it will improve the performance. So we can say delta sigma modulations is advantageous over the delta modulations because it is eliminating the accumulator at the receiver end. So it will give us simple circuit. Now we can see some differences. We can compare the pulse code modulations with the delta modulations, with the adaptive delta modulations, with the differential pulse code modulations. When we have seen about the delta modulation, what we are saying, we are supposed to send the data that will be 1 bit per sample, but we will get the noise. These are nothing but we are saying as a granular noise and the slope overload. So we can say over the delta modulations we can use adaptive delta modulations where we can vary the value of step size. It means what? Adaptive delta modulations will be advantages or the version of the delta modulations, but here when we are supposed to use delta modulation, at that time we will get the quantization noise, slope overlaid noise, that will have high sampling rate. So in order to require many times Nyquist rate that will be greater than 2 FM, because we are saying when we are supposed to use sampling theorem, Shannon theorem, Nyquist rate, at that time we will require the frequency that will be greater than 2W, 2 FM maximum. So we can say this will require higher bandwidth, so it will defeat the purpose of the delta modulations. To avoid the slope overload, we can use variable step size. So if we are doing the transmission of 1 bit per sample, and if we are using variable step size, at that time we can say that type of modulation as adaptive delta modulation. The circuit diagram of the ADM transmitter, ADM receiver will be like a delta modulation, but here additional part that will be the step size controller. It means what? Here we can vary the value of step size. When signal is varying slowly, we can have smaller step size, and when we are varying the signal faster, we will get the step size that will be higher. So we can say the comparator at the input compares the sample value, that will be, it will compare sample value with the predicted version of the previous value. But here the gain block controls the, here there is one additional part in the adaptive delta, there will be the variable step size, or we can say step size controller. So here the gain block controls the variable step size, and step size is varied based on past value. So here we can vary the value of step size. So the ADM algorithm for the step size adjustment we will follow, and here we can reduce the value of slope overload. So here we can say adaptive delta modulation reduces the slope overload, but at the cost of increasing quantization noise. It means what? It will be used to reduce the slope overload, but it will increases the quantization noise. Since ADM uses the large step size for wide variation in the signal level and the small step size for the small variation, it has wide dynamic range as compared to the delta modulations. But ADM can operate at much lower bit rates than delta modulation. It means what? If we are having the delta modulations 32 kilobytes, 16 kilobytes, with slight degradation in performance, we can use adaptive delta modulations, because it will reduces the granular noise, slope overload noise, but only it will increases some quantization noise. So we can say the advantages of the adaptive delta modulation over the delta modulations, like it is less costlier than the pulse code modulations. Dynamic range of ADM is better than delta modulations because of variable step size, variable delta. Because of reduction in slope overload, its signal to noise ratio will get improved. Bandwidth requirement of ADM is reduced because here we are removing the slope overload. Its hardware is simple as compared to the pulse code modulation. It is less costlier as the PCM. It's less costlier as compared to the PCM. It is the 1 bit output per sample. So here we can say we can use the adaptive delta modulations as compared to the delta modulations because it will reduces the slope overload. If you compare ADM, adaptive delta modulation, with the pulse code modulations, it will less costly and it will require simple hardware implementation. So now we can compare pulse code modulations, delta modulations, adaptive delta modulations, differential pulse code modulations. So in pulse code modulations, if you see about the first, we will compare these modulations in terms of number of bit. So we can see in pulse code modulation that will use 4 bit, 8 bit, 16 bit per sample. But in delta modulation and in adaptive, we are supposed to use only 1 bit per sample. In differential pulse code modulations, bit can be more than 1 or but are less than pulse code modulations. We can take more or less than the PCM. It means what? Here we are supposed to take number of bits that can be more or that can be less as compared to the pulse code modulation. If you are talking about the level and the step size, the number of level in the pulse code modulations will depend on the number of bits and its level size is fixed. But in delta modulation, step size we can keep fixed and we cannot vary that. But here we are saying in the adaptive delta modulations, we can vary the step size. It means what? According to the signal variation, we can vary the value of step size. But in differential pulse code modulation also, the number of level is fixed. It means what? Only we can vary the number of level in the adaptive delta modulations. If we are talking about the quantization error and the distortion, we can say the quantization error will depend on the number of level in the pulse code modulations. But in delta modulation, we will get the noise. These are nothing but slope overload and the granular noise. So in delta modulations, we will get slope overload distortion and the granular noise are present. We can remove these noises, slope overload, in the adaptive. But if you see, there is a addition of quantization noise. So we can say in the adaptive delta modulations, quantization noise is present, but other error, these are nothing but granular and slope overload, these are absent. But if you talking about the differential, we can say slope overload noise and the quantization noise both are present in the differential pulse code modulation. Now we can see about the transmission bandwidth. In the pulse code modulation, we will require highest bandwidth. Since the number of bits we are sending per sample, these are high in the pulse code modulations. But in the delta modulations, we are supposed to transmit only 1 bit per sample. So we can say it will require lowest bandwidth. In adaptive delta also we are sending 1 bit per sample. So it will also require lowest bandwidth. If you are talking about the differential pulse code modulation, you can say it will require the bandwidth that will be less than pulse code modulations. But that will be higher than the delta and the adaptive delta modulations. Now we can see about the difference between the pulse code modulation, delta modulation, adaptive delta, differential pulse code modulations about the feedback. So here in the pulse code modulation, there is no feedback in the transmitter and the receiver. But in delta modulations, in the adaptive delta modulation, in the differential pulse code modulation, feedback will exist. In the delta modulation, feedback will exist in the transmitter. Now we can see about the complexity of the implementation. As in pulse code modulation, we are supposed to transmit the data. Number of bits we can transmit per sample. So here its sustain is complex. But in delta modulation, we are sending only 1 bit per sample. And if you are talking about adaptive, there also we are sending 1 bit per sample. So here the circuit implementation for delta modulation and adaptive delta modulations will be simple. Also, if you are talking about the differential pulse code modulations, bit can be more or less than the pulse code modulation. So here we can make the circuit simple as compared to the pulse code modulation. So here we have finished about pulse code modulations, delta modulations, adaptive delta modulations, Then we have seen about the differential pulse code modulations and adaptive differential pulse code modulations. Now we are supposed to study about the linear predictive coder, which we will see in the next session. Thank you.